Manitow Valley.
This meeting is being recorded.
It's the story of our valley, and it's really the story of the planet. I mean, a story of the planet, not the story. And it's taken a lot of blood, sweat, and tears by humans to figure out the little that we know about the evolutionary story of the planet. And I think it has a lot to say to our lives and our well-being. So it's not just the geology of the Manitow Valley. And I might also say that this story has been greatly enriched for me by paying attention to the discipline known as Big History. So I'm putting in a plug for Big History. You can Google it and you would find a Wikipedia page and 100 pages. It's just the evolutionary story. It's the evolutionary story of the Earth and life on Earth, Big History. But it's with a little orientation. There are some themes. One of the themes is increasing complexity over time. And we'll talk about that. So I wanted to start with these beautiful towers, Liberty Bell and Early Winter Spires, made out of granite. And the mystery of our planet, the mystery of geology, because these are made out of granite. Granite cools from molten rock.
This is kind of a silly thing.
Was that anything that?
I think somebody's not
attend to that
muted.
comment.
I'm trying to mute everybody.
I see, it's
Sometimes
just
people forget.
conversation. Well, the mystery of granite is it has to cool deep underground. It's crystallized rock, which means it cooled slowly. And looking it up online, actually, I'm not a geologist. If I'm anything, I'm a botanist or a naturalist. But anyhow, we can all learn about these things. Granite has to cool a minimum of 20 miles underground for it to have the time, the several million years, I think it said 20 million years, for it to cool and crystallize so that you have discrete crystals of quartz and mica and feldspar. And yet here it is in our face. And not only towering up into the atmosphere, but carved by something, smoothed by something. And that something is probably mostly the last glacial advance, 18,000 to 14,000 years ago, of ice pouring over Washington Pass coming down from Canada. But that was only one of 20 glacial advances. And nobody knew anything about this prior to, I would say, 1800. That is the astonishing thing to all this information to me, is that humanity is just waking up to how dynamic the Earth is. And there are many good books. And I actually meant to bring down, I would say, not this book, this is a book. I meant to bring down A Brief History of Nearly Everything by Bryson. I just read it for the third time. I just couldn't recommend it too highly. It's easy reading, humorous, and so well done, and has this evolutionary story in it. So Marcia Bjornerud is also doing a good time. She has this book, Timefulness. So things get a little intricate, we'll say, avoiding the word complicated. We're still on the first slide, and we're trying to talk about the geology of the Manitow. And this question arises. So some of you know who Greg Student is. Those of you who aren't in the Manitow don't know. So he was on the board of the Cleveland Museum of Natural History. He lives in Ohio, but he has family here and he comes here. They found a new dinosaur in Ohio, and they were all excited on the board of directors at the Cleveland Museum. And Greg raised the question, so what? We don't need another dinosaur. I just like that question, so what? We need to know the so what of things. But what we do need to know is how to live on the Earth. If you think of the ecological problems that we have, the dinosaur is less relevant and ecology is more relevant to the future. So I'm just going to briefly mention, actually, Bjornerud, the author of that book, she has another book called The Story in the Rocks. She brings up this question is, so what? So what does this evolving story of deep time that geology transmits to us, that the Earth is not 2,000 years old, that the Earth is billions of years old. she says her comment in her books, she goes to mindfulness, to Buddhism and mindfulness, and says what we really need to do is to remember to observe the world. She says, remembering to observe the world is the first factor in the first of the 7 factors of enlightenment. What I like about that is, if you want to be enlightened, all you need to do is pay attention. So there's more to the story. There's more to the story, to geology, than just the rocks. There's how our minds take the information. So this is a geologist in Seattle. I forget the J. I think it's probably John Figge. He has a good book online on the geology of the Pacific Northwest. Geological understanding offers perspective which changes the way you perceive time, the world, your relationships. It's a remarkable state of awareness that just comes from contemplating rocks. It's just a nice statement about geology. So this information didn't come easily. There is something about the human mind that is a storyteller and a myth maker, and then we become invested in these myths and will fight to the death to maintain the myths which are mythological. So Giordano Bruno was one of the first people in the late 1500s to, he said, you know, the wisdom of the time was that we lived in an earth-centered universe, and this has so much, too much to say to our own lives, that there is something about the way the human mind works, and it would be just natural that it is self-centered and that we see the world through this self-centered lens. And the world turns out to be vast, and moving out of the self-center enriches our perception of the world. So Giordano Bruno came to the awareness in the late 1500s that actually the sun did not revolve around the earth, but the earth revolved around the sun. He was considered a great heretic by the Catholic Church, and they burned him at the stake in the year 1600 because it's been so painful for humanity to realize that we are not the center of the universe. The same thing happened to Galileo. They didn't burn him at the stake, but this was only 33 years after Bruno was burned. Galileo said, actually, he developed one of the first telescopes, and he said it's a heliocentric universe. They didn't know we didn't even know we were in a galaxy at the time. We didn't know what those little points of light are that's shown in the night. Although Bruno said they were stars, and that was one of his sins, that those bright lights at night are stars, other suns. And as you know, remember, Galileo was condemned to house arrest for the rest of his life. 1933 until he died about 15 years later for speaking the truth, because it contravened the myth-making power of the human mind that puts us at the center of the universe. I don't know the year of this. I would say it's about 1450. No, yeah, probably before 1492, before Columbus discovered America. This is a picture of the Mediterranean. That Mediterranean is here, if you can see the pointer. That's the Mediterranean. Well, the interesting thing about it to me is Mediterranean means center of the earth. That's what the word means in Latin, Mediterranean. The people in the Mediterranean thought they were the center of the earth because everybody thinks they're the center of the earth. And the bad news is we aren't. But that's also the good news, because trying to maintain that center is agonizing. So humans have had to figure out everything we know, and it is one of the stupendous redeeming qualities of our species is that we have figured out accurate aspects of the earth. And some of the geological story began to be unfolded by a Scottish scientist named James Hutton in the late 1500s, late 1700s. He just was observing. He was practicing the first stage of enlightenment. He was observing the planet. And one thing he observed, and that's what that film that I have recommended is about, by Ian Stewart. first of those 3-part series. I forget the title at the moment. It's about James Stewart. And James Stewart, the first thing James Stewart observed was that sediment was constantly running to the sea, constantly. He had a farm, sediment constantly running to the sea. How could there be mountains if sediment was constantly running to the sea? The mountains should wear down and the earth should be a flat plain. And then he found this place, Siccar Point, on the coast of Scotland. And he observed that there was sedimentary rock that was pointed straight up in the air, right here, straight up in the air. Sediments are never laid down upright. And then there was a layer of pebbles between, and then there was horizontal rock. And he, for one, realized that there was some great dynamic process going on that had uplifted the sedimentary rock and then worn it away and then laid down another layer. And this would take time, and that the earth could not be, as the church was claiming, 2,000 years old. It needed a lot of time. And another insight of Hutton's was that this had not happened just once, that the earth constantly cycled the rocks of the earth over and over again. Raised it. He didn't know how, somehow raised them up as mountains. They were eroded down into the ocean. They were bent by some force that he didn't understand, but he was able to interpret this. So it was tremendous insight. Yeah, so glancing at my notes, there's just such interesting information, and I can't remember it all, but so remember that Galileo had said it was a heliocentric universe, and he was condemned to a house arrest for the last 15 or 20 years of his life. It was not until 1984 that the church apologized and said Galileo was right. The fascinating thing about all this is we are just waking up to the real world and dispelling the myths that control our minds. So I don't know about, and speaking of myths, we have this problem that science says that it was kind of a joke at the bottom that somebody said, so first there was nothing and then it exploded. And that is, in a way, that could be a characterization of the Big Bang, that everything in the universe was condensed into a singularity smaller than the size of an atom. That is what science says. And it did somehow came apart and it expanded into this almost the full size of the universe in a few seconds. And so there's two interesting points here. One is, in my mind, and this has become important to me, science has a way of dispelling the awesome and mystical qualities of our lives, and our planet and our universe by pretending that it explains everything. It's like, oh, I see. There was a singularity the size of an atom, smaller than an atom, and exploded into the universe. I get that. It's incomprehensible. So Terence McKenna, who was a somewhat well-known biologist, says, it's the limit case for unlikelihood that the universe would spring from nothing in a single instant for no reason. I mean, he's just pointing out the insurmountable paradox. He says, if science gets one free miracle, I say everybody gets a miracle. So we have countercurrents here, because I'm dispelling the myth of religion, but I'm also questioning the power of science to take the mystery that surrounds us. And that's not the only mystery. And I actually took a few notes here, but I don't know if I can find them. You know, we don't know that you can find physicists who will say, we do not know what gravity is. Every object in the earth in the universe attracts every other object. We don't know why. The origins of life, biology has never, ever come close to explaining how life originated, and it appears to have only originated once. It appears that all organisms on the planet are all related, and any simple, so-called simple organism, one-celled organism, is more complex than a 747. It would have to assemble itself. I'm just saying. So science just says, well, life appeared. I would call it a second miracle. Furthermore, everything is just right. And so science acknowledges this and science calls it the Goldilocks effects. And a simple one, there are many. I've started a list actually just recently, and I have a lot of notes on Goldilocks. I'm up to 21, and my feeling is there would be no end. They might be infinite. And I unfortunately probably won't be able to remember too many, but one is that the Earth just happens to be in the habitability zone where at least water, where it doesn't get too hot, it doesn't get too cold. So Goldilocks would be fond of that. And water can exist as a liquid and as a gas and as a solid all at one time, which is utterly critical for life. Probably all three forms are critical for life. So that's we just happen to be in the habitable zone. That's a first Goldilocks effect. So I put this up just to reiterate. This is a NASA visual, and they are talking about the Goldilocks effects, that everything is just right. Well, let's see. I have a list of 21. Can I think of one or two more? They say that the expansion of the universe, the rate of expansion from this apparent Big Bang, which is, it's not that the universe is not expanding, and that is one of the great sources of evidence. It's expanding out, and if you wind it backwards, it goes back to a center. So it does look like the universe expanded from one point. If the rate of expansion were infinitesimally faster, then gravity would not be strong enough to pull elements together to make stars. If it was expanding slower, it would recollapse on itself. It's a Goldilocks effect. That's two, habitable zone and the rate of expansion. There are many, and it's just mysterious. It's just mysterious. We live on a mysterious planet. Well, actually, this looks complicated, but this is where the whole thing gets a little easier for me. So I took chemistry. I went back to school in the 80s, mysteriously, in the University of New Mexico. I don't know what I was doing there because I came to the Met House in 1970, but what I'm thinking of is I got a C in chemistry. I barely survived chemistry. And some of the stuff, which I don't remember them teaching me, seems so simple now. We're going to go through the most basic chemistry. And I swear to God, it is so easy to understand. It's easy to understand the dynamics. It's impossible to understand the why. Hydrogen, the most basic element on the planet, has one proton and one electron. The electron spins in what we like to call a shell. It looks like a shell. A better word's an orbital, because it's all over the area around the proton. But we can call it a shell. We can get away with that with minor apologies. It has one electron. So that first shell, one of the great mysteries of the universe is not only that these atoms exist, and by the way, another Goldilocks effect is that protons are about 2,000 times larger than electrons, but they have exactly the same but opposite charges. So they're perfectly balanced, in spite of the fact the proton is so much bigger. Has one electron in that shell. We call it the first shell because other elements have more shells. The first shell holds 2 electrons, but hydrogen only has 1. Hydrogen is not completely comfortable in its skin. It wants electromagnetically speaking, it has a draw to join with another element to fill its electron shell. So, well, here's a picture of electron shells. So there's a nucleus. S1 is shell 1. Shell 1 holds 2 electrons. Shell 2, S2, 8 electrons. Shell 3, 8 electrons. It's not unreasonable to ask, where did this come from? We very much dislike the term intelligent design. I am not fond of it, but the universe is intelligent. The problem in my perception with intelligent design is then we immediately concoct an anthropomorphic myth and create a God that looks a lot like us, usually male, who lives in a cloud. It's just absurd. We do not know why the universe has the level of intelligence it has. We do not know, and we will probably never know. In any case, the first shell holds one electron. It wants two electrons. How can a hydrogen atom satisfy its hunger for a second electron? It can join into a union with another hydrogen atom, share the electrons, an H2 molecule, and then it's electrically balanced and it no longer wants that. This is true for most of the elements on the periodic table. Their shells are not full. This is an inherent design of the universe. What does this have to do with the geology of the Met House? This is how the rocks form. This is how the rocks come together. It's all about the electron shells. So here's that hydrogen atom. It's satisfied. Let's see. Here's oxygen. So oxygen has 8 electrons. 2 go in the first shell and it's full. 6 go in the second shell, but the second shell holds 8. It wants, electronically speaking, it wants 2 more electrons. It will join into an electrochemical union with other atoms to fill that shell. Well, how about if that hydrogen, those 2 hydrogens joined with the oxygen? Then we'd have what I like to call OH2. Water is a naturally evolving molecule of the universe. It's just totally natural. See, they share those electrons. Hydrogen now has its one and only shell filled. Oxygen has its second shell filled. So the big history has themes, and that's really part of to me, the beauty of this big history story, the evolutionary story. It's the evolutionary story with themes. The first theme is complexity. The universe naturally complexifies. It's built into the structure of the atoms to join with other atoms and complexify over time. And it said at the beginning of the Big Bang, the only elements that existed are hydrogen and helium and a tiny amount of lithium, the third element on the periodic table. Well, just look out the window now. It's complexified. So let's try one more. So here's silicon, which has 14 electrons. The first 2 electrons go in the first shell, 8 in the second shell. Well, there's only 4 left over in the third shell. Well, the third shell also holds 8. So what could it join with? How about if it joined with oxygen? Oxygen wants 2. Silicon wants 4. So how about 2 oxygens? So we could cook up something called SiO2. It's called quartz. They just naturally form. They just naturally form when conditions are right. Those elements will join together and form quartz. And this is the story of the evolution of the planet and the evolution of the geology of the Met House. The amount of quartz on the planet has increased over time because conditions have to be right for these elements to join together. And this also explains the structure of the periodic table, how it was put together. So I typed in up there, up top, that column is all those elements are missing 2 electrons in their outer shell. So there's oxygen. We talked about oxygen. Below that is sulfur. It's missing 2 electrons in its outer shell. SE, it's probably selenium. I'm not sure. I should have looked it up. But there are others. So I just pulled up over on the right. Those in the red column are noble gases: helium, neon, argon. Their shells are full. That means that they are inert. They don't react with anything. All the other elements are hungry to react with other elements and create and to complexify into molecules. Missing 1 electron over there on the left, missing 6 electrons. Well, maybe they should meet some elements that are missing 2 electrons and form molecules. So, I'm trying to remember who said this. I forget where I got this. It might be out of Short History of Nearly Everything. Oh, no, but so this is just a statement, but it's a statement by a biochemist who won the Nobel Prize in Chemistry, Christian Deboude. There is no shortage of ordered self-assembly in the universe because of what we've talked. It's because of these electron shells. That's why it occurs. But the electron shells are a natural phenomenon, orderly phenomenon of the universe, and we have no idea how this could be. But this has led to the evolution of the rocks on planet Earth. There were almost no continental rock early in the Earth, which is over there on the bottom left, that red line at 0. There were just some terrain sticking up. Continents have evolved over time because of this attraction, and because conditions have to be right for atoms to join together, to form molecules, and to form minerals. Conditions have to be right. Well, the Earth proves to be very dynamic, and so this is a little complex. It's a graphic of something called Bowen's reaction series. It's the simplest version I could find, and what it shows is how minerals change over time due to temperature. So over on the upper right, it says ultramafic, and I always have to remind myself what mafic means. All it means is magnesium and iron. Well, magnesium and iron are big elements. They have a lot of protons in their nucleus, and therefore a lot of electrons. They're dense, they're heavy. The core of the Earth is thought to be magnesium and iron because it's so dense, gravity pulled them to the center of the Earth when the Earth was molten. Ultramafic, that's what ultramafic means. Down at the bottom is, I didn't circle it, down at the bottom is felsic. Felsic just means, basically it means silica. It means feldspar and silica. Silica is, we just talked about, silica is SiO2. Silica is mostly oxygen, and silica, SiO2. It's quartz. I'm sorry. So the thing is, these, over here is high temperature. Down here is low temperature. These rocks will solidify. The high magnesium and iron rocks will solidify first at the highest temperatures. They migrate out of magma, molten rock. They migrate out of molten rock first. Silica is the last to migrate out at a low temperature. But the opposite is true too. If the rock is already molten and cooling, the cool temperatures are going to happen first, and silica will migrate out of a cooling magma before the ultramafic rocks will. So what do we have on the planet? We have these mid-oceanic ridges running down. We didn't know this. We didn't know this until 1950. That's only 50, 70 years ago. This is all new information about the dynamics of the Earth. We didn't know there were mid-oceanic ridges down the middle of the Atlantic and also in the Pacific, not quite in the middle, where magma is pouring out of these rift zones, rising from the mantle and cooling and forming ocean crust and pushing the ocean crust apart because more and more ocean magma is constantly rising. Well, it's going to cool from low temperature. The low temperatures are going to cool first, and it's creating more high silica rock over time. High silica rock is less dense than low silica rock. High silica rock is less dense than ultramafic rock, and it floats on top of the more dense mafic rock and creates continental rock. So continental rock has been created over time. And the rock, this is one of Sutton's great insights. This doesn't happen once. This happens repeatedly. These rocks are then subducted back down into the mantle and reappear over very long periods of time. But the Earth now has a lot of time. The Earth is not 2,000 years old. The Earth is 4.5 billion years old. This could be considered another Goldilocks effect. The only elements on the planet, no, excuse me, in the universe after the Big Bang, hydrogen and helium. Do I have something here? I pulled up that lightning bolt to represent energy. So in the early universe, all there was hydrogen and a little bit of helium. Our sun is fusing hydrogen into helium at a rate of 600 million tons per, guess what, second, per second. This is incomprehensible. The sun is 93 million miles away from the Earth. We receive 1/1000th of the sun's energy. That energy is coming from hydrogen fusing itself into helium. Hydrogen has 1 proton, helium has 2. There's just enough heat and pressure to push hydrogen atoms together and create helium. It gives off a tiny amount of energy. It's less, a tiny amount of the energy is given off at the mass of the hydrogen turns into energy. That was Einstein's great insight. Energy equals mass times the speed of light squared. I don't know where that comes from, but it's true. So, but it's a small amount of energy is given off. We call it the sun. We call it heat. We're waiting to reach the solstice here in the Met-How, so the Earth will start to tilt back. Okay, so there's no longer just hydrogen and helium in the universe. There was only hydrogen and helium, a little bit of lithium. Now there's 92 naturally occurring elements. Where did they come from? They were fused in stars. Everything up to iron down there at the bottom, which has 26 protons in its nucleus and 26 electrons, they were all fused in the heat and pressure of stars. I should have looked up, I forget. I think it's something like 15 million degrees in the center of the sun. Fahrenheit. The pressure, I should have looked it up. It would be incomprehensible. It would be 1,000 school buses piled on top of one another. It smashes these atoms into larger atoms, but they only get to iron. And in iron, it doesn't get any further. And I don't think it's quite the next slide. So the sun has been creating these elements that then make up the planets. You cannot have planets. You cannot have geology of the Met-How without nucleosynthesis in the center of stars. You cannot have an Earth if the universe is 2,000 years old. We need time. And it wasn't the human mind that made the time, but the human mind had to fight for the time. And people were killed for saying that the universe was, I think Hutton said we need at least 700 million years. The universe is now thought to be 13.8 billion years old, partly because it takes time to synthesize the larger elements from the smaller elements. So there would be no planets. There were no planets in the early universe. They have appeared over time. And so the Earth is made out of the debris left over after the sun formed. And the information that I read is that 99.9% of the elements present when the solar system formed are in the sun. The remaining 0.1% forms the planets that now orbit around the sun. So it accreted over time basically from garbage that had gone into orbit around the sun because of gravity, in part. To some degree, it's a similar story with the moon. The Earth originally had no moon. This is the scientific story, and it's the best we know. It's almost surely true. I would say 99.9% true, but we're trying to interpret something that happened 4.5 billion years ago. A planetesimal smashed into this Earth and blew part of the Earth's crust out into space, and it created the moon. And so if it was created out of crust, it infers there would not be much mafic material in the moon, and that seems to be true. Mafic, remember, magnesium and iron, they migrated to the center of the Earth. So it blew part of the Earth's crust out into space, and that went into orbit around the Earth and then accreted into the moon. Well, that is a serious Goldilocks effect, because that is why the Earth is tilted at 23 degrees. Because it was hit by a planetesimal. Otherwise, it would have, those pieces of solar dust that had gone into orbit around the sun and then accreted into the Earth would have accreted perpendicular to the sun, but it was knocked over at 93 degrees. That's why we have a moon. Well, the collision with a planetesimal, as shown in that picture, is why we have a moon. The collision is why the Earth is tilted at 23.5 degrees. That's why we have seasons. The moon is why we have tides. there are other effects from this collision. And this is a theme on the Earth that has come to be a point of interest to me. Ann Diamond, I don't know if she's here today, but she sent me a picture last week from the Ngorongoro crater in Africa, where she must have been 2 weeks ago. So it's this gigantic volcanic crater. The picture was full of hippopotamus and wildebeest, this incredible richness of megafauna that had come, that were living in a place that had experienced this tremendous cataclysm, the explosion of that crater. That crater must be 20 miles across. And that same thing then is true of the Yellowstone. Yellowstone Park is one big crater that when it blew, the biggest explosion that we know of, which I think was 2 million years ago, it left 2 feet of ash in Nebraska. And if you go to there now, it's the only place left in North America that's full of megafauna. So these cataclysms, somehow the universe translates them into a flowering of more richness. It's a great mystery, a supremely beneficial collision. So I pulled up on the left down at the bottom, what if there were no moon? I want to point out that the Meta Naturalist does deal with these evolutionary stories. The first, not constantly, but we're fascinated by this evolutionary phenomenon of life. The universe growing richer over time, the elements appearing out of the first 2 elements, and then life appearing. So that's a plug for the naturalist. So getting to geology, checking the clock here. So, we can start off, geology is very difficult. I have a hard time going out and looking at the rocks in the Methow and figuring out what they are, but it does start simply. There are 3 basic types of rocks. We do know this. Igneous rocks means igneous means born of fire. And so igneous rocks have been totally melted. They either appeared on the planet as volcanic rocks on the surface, which means they would cool immediately, or intrusively, like that granite we talked about, in which case they cool slowly. What else do we have? Metamorphic rocks, the word metamorphic just means changed form. That's what the word means. Metamorphic rocks have been heated to a point where they were plastic but not molten, and so they have stretch marks, literally. They're underground, the pressure of the earth is pushing on them, and the minerals migrate in a certain way that creates these wavy lines. So we can identify the 3 rock types. At least we can start there. Clastic just means fragments that have been glued together, and those can be large or small. So that's what the Methow. So this is a stratigraphic column of the rocks in the Methow Valley. This is available. I think I don't know if I still have it at the Methow Naturalist, but probably it's still there. You can download it, but it is interesting. These are the stratigraphic layers of the Methow Valley, starting with the Twist Formation down here. It says Twist FM, Twist Formation. It's 4,000 feet deep. It's 160 million years old from the Jurassic period. So the interesting thing about Twist Formation is there would have been dinosaurs at the time, an interesting thing about it. And then these other layers appeared, and some of the information there, how old they are. The youngest is the Pipestone Formation up here at the top. It's 2,000 feet thick. We'll talk a little more about it. There's a wavy line right here. It's a little hard to see. This is a wavy line. It's an unconformity. It's like at Sicker Point. There are rocks missing, and science has, to some degree, the geologists figured out how many years of rocks are missing. I actually can't see that, but it says 20 or 30 million years of rocks have been worn away before the next layer appeared, which is just now the top sediment. But there are other unconformities here. There's an wavy line. I think that says 6 million years between Hart's Pass and Virginian Ridge. It's not a steady process. It's a dynamic process of upbuilding and wearing away and upbuilding and wearing away of the surface of the earth, which was James Hutton's great insight in about 1800, but still that's not that long ago. These are what the rocks are made out of. These can be interpreted. There's little V's in here. I know this is too small to see, but there is a lot of volcanic rock in, surprisingly to me, in the Met Hal. It's mostly volcanic and sedimentary rock in the Met Hal Valley. Circles there. So this is a little joke about plate tectonics. These are two continents splitting apart. Do continents move or don't they move? This is new insight in the last 100 years. I think, it was several centuries ago, people suggested that maybe they moved. There was no scientific evidence. Alfred Wegener was one of the first to start to accumulate evidence that continents had been together, the fit of Africa and South America. They fit together perfectly. Well, it turns out that the stratigraphy on the coasts of those also fit together, and they clearly were together. The fossil record between Africa and South America also fits together. So I think here's Wegener. He put out a book, I think it was in 1916, 100 years ago, that the continents had moved over time, and he was raked over the coals for putting that out, because no one could, I don't know why they couldn't figure out a mechanism. How can you move planets? We knew about volcanoes. We knew that there was a molten core, but they couldn't figure out that heat in the core was causing the Earth's crust to move around. In any case, Wegener was one of the first to put out scientific evidence. He died in 1930 in Greenland, still working on his theory, which he called continental drift, which I remember actually when I was in school. We called it continental drift in the 50s and the 60s. And it wasn't until 1970, around 1970, that the scientific community began to accept that the continents moved. And trying to think of an author, the Basin and Range, what's his name? He says in 1980, still about a quarter of geologists on the planet did not accept that the planets move, but it was in. So some of these details are in my notes, and I'm reticent to go looking for them.
The author is John McPhee.
Yeah, John McPhee. Thank you. So many details, cannot remember them all. So due to some oceanographic work that was done in the, I don't know if it was because of World War II or just during World War II, it was first figured out there was this mid-oceanic ridge down there. You can see it down the middle of the Atlantic Ocean there, the red line. It's not quite so centered in the Pacific. That there was magma coming out in the middle of the mid-oceanic ridge. And then in the early 50s, work was done on aging the rocks in the oceanic crust. And it was found that the rocks near the ridge were youngest and the rocks furthest from the ridge were oldest. The oldest rocks were 200 million years old, and then they disappeared. There were no rocks older than 200 million years old. Where could they be going? It came to be understood that they were disappearing, subducting under the continents, and that the continents were on these plates that were moving as well as the ocean crust. This is, here's a diagram of that process, I think. So here is magma coming up from the Earth's mantle, melted rocks, pushing out onto the surface of the Earth, cooling and pushing the ocean crust to the east and to the west. The crust comes up against the continental rock, which is made out of different material, as we talked about a bit. It's more high silica, it's less dense, it actually floats on the oceanic crust. Oceanic crust is much more mafic, magnesium and iron. It sinks under the crust and is remelted and is cycled. Everything on the planet is cycled. That's one of the things humanity has yet to fully realize. You know, that's called ecology, that everything is related to everything else and everything cycles. But the question arises, I think maybe I put it in here, why is the mantle molten? The mantle is up to 6,500 degrees Fahrenheit. How's it possible? Where's that heat coming from? And the answer to that question is radioactive decay of the elements at the far end of the periodic table, like uranium and a few other radioactive elements, probably starting with radon at 86, protons and electrons. So these protons, they all positively charged. Uranium has 92 positively charged protons in the nucleus. Positive charges repel one another. I don't know. I'm sure a few of you probably know more about this than I have. Never understood how this could be, but they say that they just made up a force. Do we know what that force is? They say there's a force called the strong force. They just call it the strong force. It's also a weak force. There's strong force that holds these protons together. But you get up to beyond 90, and those elements cannot hold themselves together, and they spontaneously fall apart slowly. They give off elements, radioactive elements, that also emit energy. Energy is when these radioactive elements decay, they give off protons and energy, called radioactive decay. Well, where did they come from? They only exist because very large stars, when they run out of fuel, and we could say hydrogen and helium, the process goes beyond hydrogen and helium, but they eventually run out of fuel. They collapse on themselves, gravity pulls them together, they become so dense that they explode, and they're able to create these unstable elements that we call radioactive. That word, I think the first one that was identified was radium, and that's where the word radioactive comes from. But they go up to 92, they go up to, so it's radioactive decay in the center of the Earth, giving off energy that creates the molten core on the planet. And those radioactive elements only exist because of supernova explosions. So that is an evolutionary phenomenon. You could not have had planets and molten cores early in the universe. They had to evolve over time. So here we have a geologic process of magma coming out and the mid-oceanic ridges, pushing the ocean crust to the left and the right, subducting under the continental crust. They carry with I think I see here. Well, this is a cross section of the Met-Hal, and this process of plate tectonics explains everything really about geology, and therefore it explains everything about Met-Hal geology. This is a cross section of the Met-Hal Valley, and these formations that are on that sheet, and some of these we've heard of, and probably we've heard of all these places, and there are these formations. Twist Formation is the oldest, followed by Buck Mountain. It says K, so it takes some interpretation. K is for Cretaceous, but the C had already, Cretaceous is spelled with a C, but the C had already been taken by Carboniferous. So they use a K to represent the Cretaceous. And then it says N, that's a Newbie group. So Twist and Buck Mountain are combined in a group called the Newbie group, but this is the Twist Formation. Here's VR, Cretaceous Virginia Ridge, the Virginia Ridge Formation. These are highly visible in the Met-Hal Valley. We'll look at a few pictures of them, but they're smashed. Why are they smashed? This is volcanic clastic debris, fragments of volcanic rocks laid down as flat sediments and ocean sediments. A lot of the Met-Hal is made up of ocean sediments that have been smashed. Why were they smashed? They were smashed between two continental masses of rock. The continent itself and a smaller structure that we call terrains, which are going to come up here pretty soon. We need a picture to get to this. So here is the continent, North American continent, which may be, I think the North American continent is being pushed to the west by subduction on the Atlantic coast, the spreading of the ocean crust in the Atlantic. It's moving somewhat to the west. Here is some crust coming eastward, ocean crust coming eastward. It has some continental rock embedded on it, and we call that a terrain. And that terrain is going to be pushed up against the continent. It is going to smash this sedimentary rock. And here it is smashed down here, and we call that the Met-Hal. And that is the origin of the rocks in the Methow Valley. It's all about plate tectonics. Everything is explained by plate tectonics. And here are those smashed ocean sediments. We call it the Twist Formation. And this is a half a mile from the Winthrop Post Office. When you leave the Winthrop Post Office, traveling towards Twist, and you go to the top of the hill, if you could stop your car there, you could enjoy this incredible geologic wonder of the Twist Formation sticking out in the road cut at the top of the hill. The problem is the cars are going 65 miles an hour, and it's hard to stop there. You can do it. You take a look. If you look carefully as you go by one time, you can find a place to pull out. You can climb up on the other side, on the east side, and look over to the west at those rocks. They are beautiful. So these are the rocks of the Methow Valley. This is actually at Bocky Hill. This is actually Bocky Hill showing just slightly right here behind, but you can't see it. But Bocky Hill is Pipestone Formation. I can see it out my window right now, but it's on top of this Buck Mountain Formation. And if we could see that stratigraphic column I showed, there's like 20 million years of rock missing that got worn away because this process is so ancient. There is this good map that a Methow Natural subscriber made for me, and you can get it if you want it for $25 because that's what it costs to print it. That's Twistman Winthrop. So here is the Buck Mountain Formation circled. I just showing that these formations. This is Julian Barksdale's map. Julian Barksdale is the premier geologist in the Methow Valley. He worked here for more than 30 years. He died in 1983. I actually did meet him. He was a very nice man. And he figured out the structure of Methow Valley. It's Methow Valley stratigraphy, and it's a little changed in the work since then. There have been, I would say, in my mind, minor revisions. The geologists might disagree. Anyhow, to orient you, Winthrop and Twist, here's the Buck Mountain Formation. It extends up to Buck Lake and Buck Mountain, but it comes all the way down. Actually, I think, this darker green is the alluvium of the rivers. This is the Methow River. This is the Chewok Twist River here. Anyhow, it's a fun map. You can really, and you can go out, you can take it to the field, and start looking for these rocks. So Hartz Mountain Formation. So the interesting thing, this is taken from the Hartz Pass Road. And interestingly enough, the rocks on the Hartz Pass Road are not the Hartz Pass Formation, they're Virginian Ridge. And you can get that off that map, but you can see the Hartz Pass Formation, and probably I think once you go beyond Hartz Pass, it does turn into the Hartz Pass Formation, but on the way up. Anyhow, the interesting thing about this, it shows the geologic process. These are ocean sediments that are turned up almost 90 degrees. Why? Because of plate tectonics and the subduction of ocean plates like that. Smash between continent and terrain. Virginia Ridge, same thing. These are ocean sediments and probably volcanic clastic sediments compressed into sedimentary rock and then turned up on edge by the process. Plate tectonics, look at this beautiful. So these would be metamorphosed because they would have been laid down like this. They would have been laid down, well, they would have been laid down horizontal and then buried deep in the earth, a lot of heat and pressure. They just get bent by tectonic forces. And so this is on near the Hartz Pass Road. You have to hike up Cache Creek. It's a very short ways, quarter mile. Winthrop Sandstone, 100 million years old. This is at Dripping Springs. This is on the Twist River Road. So this is at Dripping Springs. You can see this if you park your car at the Dripping Springs parking lot. There at Bozo Canyon. Bozo Canyon is right here. These sedimentary rocks show up. These are terrestrial sediments, sandstone, with many terrestrial fossils in them. This is on the Twist River Road that also the Winthrop Formation points out there. This is organic matter. This is almost coal. Several of us have brought this home and tried to burn it. It doesn't have enough organic matter to burn, but it's full of organic matter enough to turn it black. So let's see. Of somebody who grew up on Squaw Creek, sorry, I forget what we call it now. It's no longer Squaw Creek. Ian. I can't think of Ian's last name. He did his
It's a
PhD
geology
on the rocks of the
The
Windsor
Mid-Ohio
Chain.
Valley is the
Yeah,
subject,
geologist.
and they're recording it. So it'd be good to show Pat when she comes.
And mute yourself.
Jim,
What?
go watch your video.
Okay.
Ian, why can't I think of his last name? He found 135 plant fossils and has beautiful examples of them in his PhD work, which went on for a number of years. He had his whole family up there prying these sedimentary rocks out. There's a big story with the Winthrop sandstone. We don't have time to tell it, but this was just a hint of the story is the Winthrop sandstone does appear to be a terrane, Terrane, that rode for more than 1,000 miles on the ocean crust and then accreted onto the edge of the continent 100 million years ago. It was probably not laid down anywhere near the Mid-Ohio Valley. And that is how dynamic geology is. That is how dynamic the planet is. Midnight Peak Formation, you can see the strata here. This is, I think, volcanic down here, the Ventura member. See, it's red. You can see it's a little different, but it still has the same distortion from its original. It would have been laid down horizontally and is now nearly vertical. This is partly from the forces of plate tectonics smashing it, and also from the fact that the Mid-Ohio Valley actually sank relative to the land around it. It's called a Graben, which is a German word for grave. And there was uplift to the east and the west, and the valley itself sank. And that's part of the reason all the sedimentary rocks in the Mid-Ohio are at near 90 degrees, except Pipestone Canyon, which is the the earliest rocks in the Mid-Ohio, except, the earliest actual rocks, 60 million years old. Well, that puts it within near range of dinosaurs, and geologists have gone here looking for dinosaur bones and have not found any. There are plant fossils in the Pipestone Formation. I should have put a picture of one in, but the notable one is the Dawn Redwood. There's a lot of Dawn Redwood fossils in Pipestone Canyon. Dawn Redwood was common fossil in many places, probably in the Northern Hemisphere in the earlier years of geology, but was thought to be extinct until it was found to be living in a small grove in a valley in China during World War II, 1941. After World War II, seeds were brought to the United States, and it now grows at the University of Washington. It grows all over the Pacific coast, always horticulturally planted by people, but it does quite well. Beautiful tree. The interesting thing about metasequoia is it's a deciduous conifer, maybe like larch, we could say. We're used to the fact that larch lose their needles, but metasequoia loses the whole last year's branch. The whole branch falls off. It's a fascinating tree. And those are the kinds of fossils that you can find, not so easily. It's easier to find rattlesnakes than it is to find metasequoia. Anyhow, we don't have much time to talk about this. There's 2,000 feet of sediment piled up here, highly varied from conglomerate rocks down here, some of them the size of Volkswagens, very large rocks rounded by water, layered with sediments of sand and gravel, and then changing back to cobbles and sand and gravel. It'd be fun to talk about how this could have occurred. I don't think we should take the time. I do not know the actual answer. I've just tried to figure out myself, because this is what naturalists do. Try and figure out how these things are, because I haven't heard a good explanation for how this occurred. Julian Barksdale, the Mid-Ohio geologist, he says it was a high energy event, Well, if you have cobbles the size of Volkswagens, you know it was a high energy event. So this is the Pacific coast of North America, mostly Canada, a little bit of Washington down there. They're all terranes. All of these were continental fragments of rock embedded on the oceanic crust that were pushed onto the continent. So plate tectonics is the story of the planetary geology and the continents. And it's been slowly unraveled by geologists. These are the Farallon Islands. They're moving north at about a centimeter or two a year. They are a small terrain. So it's like this. They're like this. They're being carried on an ocean plate. They're moving north. So you could ride them to Washington if you were patient. Chert, I thought about taking this out, but I left it in because the chert is silica. This is not in the Met House. This is a chert strata here. I forget where it is, but chert is common. There's chert in the Met House. There's nothing quite so overt as this, but it's common in various rocks in the Met House, certainly in the Pipestone Formation. Chert is made up of the shells of oceanic microorganisms like diatoms. And I brought that up because diatoms are such major players in the history of the Earth, like plate tectonics. Diatoms and other forms of algae, strange to say, diatoms, even though they make their shells out of glass, are a form of algae, and they're photosynthetic. They produce about 50% of the oxygen in the atmosphere. So they're critical to our lives, and they do come up. And we're going to try and look at, well, there is a physical class associated with this slideshow. There's not much room left in it. If you're interested in joining it on Wednesdays, send me an email. But we're going to try and look at these diatoms. It turns out if you look at the slime on the rocks in the Met House, they're covered with diatoms. I found that so fascinating. The story never ends. And fortunately, the slideshow does. And we are almost at the end. But the dynamics of the Earth are just flabbergasting. And so, yes, we all know there was this most recent glacial advance called we call it the Pleistocene, but there was not one glacial advance. There were up to 20 glacial advances in the last 2.6 million years. This is a picture of the last one. It was massive. It covered much of the northern part of the United States. It was a little thinner in our area. And, it petered out by Wenatchee. The ice did not go beyond Wenatchee, but the Methow Valley was completely filled with ice. The only thing sticking up was this is this is Silver Star and Gardner. That's a picture that I took 16,000 years ago. This is what the Met House looked like. These are a little bit of rock sticking out of the Met House. It's unbelievable what went on here. And so there's evidence. All this evidence is laid all over the landscape in the Met House Valley, and it's been interpreted by the geologists. It would be hard for us to figure it out. These are glacial erratics. Probably says that there. Doesn't say it. Glacial erratics, very common. The water, surrounded by water up on the hills of the Met House Valley. How could that be? It was actually Julian Barksdale who was the first to realize that the Met House Valley had this massive glaciation. These terraces all over the Met House Valley are left by meltwater as the glaciers melted. There are coulees. This is actually the Met House. You can't get oriented very well. I can't see it well enough to read it, but Pipestone Canyon is a coulee where meltwater ran down through, and Elbow Coulee is a coulee where glacial water eroded the canyons. There are many coulees. So there are signs of the Met House glaciation, the last glaciation, all over the Met House Valley. Here's the last couple of slides, but it's just another incomprehensible aspect of reality. North America was full of elephants just 16,000 years ago, and not one species. There were 5 species of elephants. There were several species of mammoths and a mastodon and a small mammoth that lived on the Santa Catalina Islands. And their fossils have been found all over North America. The mastodon's been found all the way down to Costa Rica. Horses evolved in North America and went extinct in North America. What happened to all these animals? Well, it's still argued a bit, but this is Clovis, a cache of Clovis points found in East Wenatchee in 1987. They were digging a water line. These are Clovis points. These things are like 6 inches long. What do you need with a 6-inch point? Well, the only thing you can stab with something that big is an elephant, it's pretty clear, it's very well known at this point that the early Native Americans hunted the megafauna and probably hunted the megafauna to extinction. So, in this hour, we've talked about this massive change over time that, to the credit of the human mind, humanity has figured this out. We have these tremendous issues that Homo sapiens is facing on the planet, but the brilliance of humanity is just astonishing. So this was, 2,000 years ago, this Roman noted, but it's just a great statement. The time is a river of passing events, strong as its current. It just never ends. We only see a small slice of it. So it looks like time is standing still, but it is not. We are part of the flow of events. And this is what we get to live with right now, this beautiful scene of the Methow Valley. But it's temporary. All things are temporary. So this program is recorded, and Met at Home posts it, and you can see it there, but you probably saw it just now. So